Good day, everybody, and welcome to our OptiMode webinar titled Polarization Splitter with Holey Fiber. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be sitting alongside your presenter, Damien Merrick. Before we begin, let's discuss the format of today's webinar. So during the presentation, we're going to have two question and answer periods. The first one at the halfway point, so about 20 minutes in, and the second one at the end. We're not going to be handling any questions via the raised hand option, so please type all your questions into the questions section only. We're also going to launch 3 polls, such as the one you're looking at now. Please take a moment to answer each one. And over on the GoToWebinar control panel, you'll find a PowerPoint handout. Please feel free to download this at any time. And finally, we're going to be recording this webinar and distributing it to all registrants via a download link that you're going to receive in an email exactly 1 hour after the webinar session ends. So you should get that by noon Eastern Standard Time today. So with all that said, I'd like to now hand it over to your presenter, OptiWave research scientist, Damien Merrick.
Hello, everyone. My name is Damien. I'm just getting the PowerPoint set up here real quick. I believe everyone should be able to see the screen now. So let's get started. My name is Damien Merrick, and I'll be presenting this webinar on designing this pretty cool looking polarization splitter that uses a photonic crystal type structure. And specifically, it uses Holey fiber. Okay. So we're going to talk first about a little bit of theory, because there's not a lot of three-dimensional diagrams of this structure, except for the one on the right that I took from the paper, that the reference at the bottom of the slide there. And so I'll show you first kind of a demonstration of coupling from waveguides, just in case you are not exactly clear what's going on. I think a nice little picture of that will show it more clearly. And then I'll just go right into the results that we got with OptiMode and compare it to the reference that I'm working from here that was designing this this polarization splitter structure. And then we'll go into some of the details of the design, and I'll show you in the OptiMode designer how to build it, how the simulation was run, and all those things, as well as looking at the band structure. I put this in here because I thought it was interesting. It's pretty easy to calculate this from OptiFDTD's plane wave expansion solver, so I threw that in there as well. And any time that's left over, I can talk more in detail about some of the techniques that you have to keep in mind when you're working on these structures that have very, well, I'm gonna say very complicated geometry, but definitely more complicated than a lot of more simpler type waveguides. So as I said before, on the right, we have the picture or diagram of the polarization splitter design. And basically it's set up so that there's 3 waveguides, and the cross-section of the waveguides is given in the lower half of that figure. And we'll see that again in the OptiMode designer. But the center one with the green circles, that's the type of waveguide that supports a single mode, but multiple polarizations. So just like a single mode fiber, it's called single mode, but actually it supports 2 different modes. One could be an x-polarized mode, and one could be a y-polarized mode, right? There's 2 independent ones. And then of course, any combination, you could have a 45-degree polarized mode that would be made up of the two X and Y polarized modes. However, interestingly, if you choose a more asymmetric type core, so on the left in the purple, or on the right in the red, that have elliptical type core, you can actually design it so that it's single mode and also single polarization. So it won't support an X-polarized mode on the left. The purple one is called the EY type core that only supports a Y-polarized mode. And on the right is the EX type core, which only supports EX polarized mode. So if you come in with this middle one that has supports for both types of modes, you can kind of split out the polarization into each arm, right? Depending on if it's y-polarized or x-polarized. So that's kind of the interesting part of this paper, was that they could make this splitter that you can give it any polarization in the fundamental mode of the green core, and then kind of strip out independently each polarization into the different arms that are alongside it. And it's not so hard to model this, actually. You can do it with mode solving, and we'll go into that right here. So I just want to talk a little bit about how you could model mode coupling. There's kind of two ways of looking at it. One is, if you think about it, if you have one sort of undisturbed waveguide, like on the top of the figure that I've labeled independent waveguide. This is a waveguide. It's a 2D waveguide, and I'll show you in FDTD how I made it up. You can think of it having one mode, and then if you have another waveguide that's identical in the bottom picture, if you bring them closer together, you can, if they're still pretty far apart, you can sort of assume that the mode shapes are not really being affected or not being perturbed a lot by the presence of the other waveguide. And you can say that you can approximate the mode structure of the two waveguide structure by using the modes of the independent waveguides as a basis. So you can see, using that sort of idea, you can create two modes, right? You can have a mode that adds up both the modes of the two independent waveguides. That's the one that's symmetric in the bottom right, that goes, that has two humps, like camel humps, I guess. And then you have the asymmetric, where you subtract one of them from the other. And then you get sort of the asymmetric type mode that goes up and then down. And these two modes actually will have different propagation constants. And therefore, if you excite them equally, they will beat. So you'll see that it'll beat between one mode and the other. And we can look at that in FDTD in a sec. I just want to say also that you can calculate, it's pretty easy to calculate the length of this beating behavior by using the equation I have down on the bottom left of the slide, where you take the wavelength times it by 0.5 and divide by the difference in the propagation, not propagation constant, the difference in the effective or modal index of the modes, the one even, one odd. So that difference will tell you how long it'll take. If you start with one waveguide that has its mode excited, how long will it take for that mode to sort of couple over to the other waveguide? And of course, the other way of looking at this is that it's just one structure. The notion of two independent waveguides, you don't even really have to care about that. It's one structure, and the structure just happens to have two modes, right? One mode is symmetric, one is asymmetric. And if you excite one arm, it should excite both of these two modes equally, because they both, on one arm, they might have equal sort of pulse shape. Here, they're kind of different, as you can tell, but they should about excite them equally. And then, but since they propagate different phase velocities, you'll get the beating behavior. So there's sort of two ways of looking at it. Sort of the super mode that's made up of two independent waveguide modes, or you can just say, I have one structure and I'm just interested in the modes that this structure has and how they're excited. So let's look at some pictures to help explain what I'm talking about. If I can go over here, and you'll notice that I have that 2D structure set up in a sort of a propagation experiment or simulation. If I go into the 2D refractive index view, you can see I have silica in the red up and bottom, and then I have air below and above and in between. And we could look at the modes of this structure. If we go into the input plane, I'm doing in 2D just to make it as easy as possible, but the same ideas also translate to 3D. We can find the modes of this structure, and this is our 2D mode solver. And it's very basic, it's very simple to use. You can select which waveguides you want to calculate. So here I've selected both of them. So we're doing the whole structure. And if I go to parameters, make sure I'm looking for, let's say, 3 modes, just to make sure I don't miss any, right? This structure has 2 modes. One's going to be the symmetric one, where the EY symmetric over the axis, and then we should have the one that's asymmetric. That's basically the negative of the other one on one side. And this will create that beating behavior as before. Now, if we go back and we say, all right, I want to use sort of the mode coupling theory to describe this propagation, you can calculate just one mode. Sorry, you can calculate one waveguide for about 3 modes. And you'll say, okay, so this, when it's one waveguide by itself, it only has one mode, only supports one mode, one polarization. But as you bring 2 of them together, you get this sort of super mode or a different structure. You can add up the 2 modes of the 2 independent waveguides to create 2 new modes, one symmetric, one asymmetric. Now, if I choose to excite this structure with the mode of one of these waveguides, one independent mode, it'll excite both those even and odd modes equally, or if it's properly set up, it should be about equally. And then as it propagates down these waveguides, they'll propagate different speeds, and then you will definitely see the beating behavior. So I've already run this simulation. It's not so long, but it's probably more fun. Just look at the results. So I designed this waveguide such that it would fit in the simulation domain. So it starts off in the top arm over here with almost full power, and then over about 60 microns, it just under 60, more like 55. You can see over here it begins to go up again in the top arm. So right about here, so about 53 or 54 microns, it's fully coupled into the other arm of the waveguide. And you could sort of see that if you just cut off the other waveguide here, you could probably get a lot of the power coupled into this other arm, right? And that's how they do X couplers, or cross couplers, I should say, and power splitters, as you saw in the BPM webinar earlier this year. And this is basically what we're going to do, but obviously the structure is a little more complicated. And another reason why we're not going to do an FDTD is because you can see here that the length of coupling can be pretty long compared to the wavelength, right? 60 microns compared to the wavelength of 1.55. You can do it in 2D in FDTD because it's 2D, it's a lot faster. But in 3D, it gets to be a bit of a longer simulation. And also, I designed this structure so that it would fit in a FDTD simulation. The coupling length is 60 microns, pretty short. The paper that we're looking at in this presentation, the coupling length is 600 microns for the same wavelength. So I hope you can realize that FDTD would not be the best tool for this job. It'll take a very, very long time to calculate that result. And we can calculate the result very accurately with a mode type approach. But this serves as an example of how it works. You select one mode, it couples to the other waveguide. So let's look at back to the slides here. Okay, one of the reasons why I chose this example was because we matched the results of this paper very well. It's a little bit amazing, actually. We almost, for the 3 independent cores, you can see them on the bottom here. So again, they have the different core structure. They have the same cladding sort of crystal structure. The green circles, they all share that structure. And they have different cores to have the special properties of only supporting an X-polarized mode or only supporting a Y-polarized mode. And then the center core supports both those modes. And the first section of the paper was trying to match the modal index of these 3 different cores, right? That helps to reduce the insertion loss of these if you're coupling from a 3-core structure into a 1-core structure. There'll be less loss at the interface. So Zhang et al. Was try to design these ellipses and other cores, and the circle cores, to get the same propagation constant or same modal index. And they achieved that pretty well by designing the ratio of the diameter, the max diameter and the min diameter of these structures. And I just took the results they calculated and plugged it into OptiMode, and I got very, very similar modal indices for these three different structures. A little bit of difference on the xpolarized mode structure, but still pretty amazing. And one, I guess, reason for that is because both the paper and OptiMode solvers use the same type of finite element approach. So that's one similarity between them. However, completely independent design of these mode solvers, except that they use the base method of finite elements. And then, of course, the final conclusion of the paper was that you can make a splitter that will split the xpolarization and ypolarization modes out of the center core. And it was calculating the lengths, the coupling lengths of that splitter. And here in the paper, they got about 638 microns for the xpolarized coupling length and 622 microns for the ypolarized. And then in OptiMode, I calculated very similar, 642 for the xpolarized and about 619 microns for the ypolarized. And we'll see more of that in a bit. In how I did in OptiMode, I just wanted to show the results right away. And I think this is actually a pretty good spot. We'll have that first quick poll. It's a good, we're not about halfway, but it's a good stopping point to have you guys take a break, answer some polls, and then I can answer some questions in the meantime. So please, Brian, start the poll here.
Okay, will do, Damien. I got the poll launched right now. And just a reminder to please type your questions in the questions section. We're not answering any raised hands in this webinar. So we're going to leave the poll up there for about 15 more seconds. And if you get any questions in before the end of that time, we'll go ahead and answer them. Otherwise, I think Damien will continue on. And just a quick reminder as well, we are recording this and we'll send out the videos. So if there's any sections that you want to relook at and watch what Damien had done, you'll have the opportunity when the video is released. Okay, I'm going to go ahead and close the poll and I'll pass it back to you, Damien.
Okay, thanks. Looks like there's not any burning questions so far. I guess we haven't really gotten to the actual design yet. So let's do that now. Let us open up one of these structures here in OptiMode. I've got one that is the results file. Give me 1 second to do this. So open up a couple just to, I've shown some pictures, but maybe it'll be a little bit more helpful to see a couple structures opened up here. So again, the first part of that paper was designing these different crystal structures so that they would get the same modal index. So they'd have the same phase velocity. And you'll see here now in this full glory, the structure we have in green, that's kind of like the cladding, or like the characteristic photonic crystal structure that's in the background. And it's common between all these different structures. Even the multi-core structure has the same type background photonic crystal. The differences being between these different structures is that they have different cores, right? So this one is the center core that has multiple modes. This one is the X-polarized type core. And then we have the Y-polarized core. So first things first, a lot of times when people say photonic crystal, the first word that pops into your people's heads is band structure, or band gap, rather, also band structure. And it's very, I think it's common maybe just think, okay, there's a band gap on this photonic crystal, that's what's guiding these modes. But that's not always the case, right? You don't just have a photonic crystal and then magically have a band gap. And that was interesting to me. So I wanted to, my first look at this paper, I wanted to do a quick look at the actual band structure of this photonic crystal here so I can have a better understanding of what's going on. And I talk about it in the paper a bit too. And it's a pretty simple structure, so I thought it'd be really quick and kind of neat to just do it in OptiFTTD. So you'll see me do live here, do a really quick band structure calculation of the structure in the paper. And so the structure in the paper has it's silica at 1.55. So I'm going to just modify this material here and call it, I won't change the name, I'll just change the material parameters. So it has the refractive index of 1.45. I'm going to change the background index of the simulation to air. Sorry, to not air, to silica, because it's a Holey fiber. And then I'm going to draw the photonic crystal structure right here. The pitch or periodicity was 1.24 microns. I'll just give a couple elements so you guys can see it. It's got a hexagonal structure. Oops, I gotta rechange these ones here. And they are basically circles, so I'll add a new type here, make sure it's waveguide channel, and the radius was, I believe, 0.403 microns. That all looks good. I'll just move it a bit more into the center here so you can see it. Maybe zoom in. And I want to change this material to air because it's holes in the silica. So I want to make sure that I'm doing that properly. I'll save this as band demo band gap Monday. And then look at the refractive index. So we have the high index silica structure with the air holes in blue there. And now it's basically as simple as going to the plane wave expansion band solver tool, and I can choose a path hexagonal because it's a hexagonal periodic structure. I can increase the mesh resolution here a bit if I'd like. Maybe the tolerance. I'm just matching the ones I did earlier so I don't get any surprises. So for one polarization, this is transverse electric polarization, which has a EY component in our domain. We see that there is no band gap really here. So at these wavelengths, there's no band gap here. On the left-hand side, it's the inverse of the wavelength instead of more like electron volt. Maybe in semiconductor physics you'd see. So our wavelength is if you inverse, it's about 0.65. So about between 0.5 and 0.7, let's say, and clearly there's no band gap for anything, for any wave vector. So there's no band gap in the transverse electric polarization. Let's see, what would it be maybe in the TM structure, maybe there's a band gap. And actually there is no band gap. There is almost one at about maybe in this area, 0.3 to 0.4 or 0.35. There could possibly be a band gap. If we increase the resolution, maybe there's a small one. But at our wavelength of interest, 0.65, there is no band gap. So this photonic crystal structure doesn't have a band gap at our wavelength. So it's not a band gap that's guiding the structure. It's something else. And I'll show you that in the next slide. Right, so I had this plotted beforehand. I did it with a higher resolution, and if you go to a really high resolution, there's actually a very, very tiny band gap in the TM structure. I'm not completely sure if that's numeric error or if it's actually a true tiny band gap. But the point is that it's actually not in the wavelength range of our interest. It's at a higher frequency. Sorry, it's a lower frequency. Our area of interest is from 0.6 to 0.7, and there's clearly still no band gap there. So what's the mechanism for guiding the light if there's no band gap in the structure? And basically, it's just because if you kind of calculate the average average refractive index, the areas that have, and I'll switch over to another picture here, maybe this one. So let's look at the purple core one here. These circles are ever so slightly smaller than the green ones. So if you look at it sort of as an average refractive index, the air holes are smaller, so the average index is larger over this core area than the cladding structure that has larger air holes and therefore will have a smaller average index. So this light's being guided by basically total internal reflection, although of course the periodic structure of the crystal is having an impact, right? I'm pretty sure you wouldn't get the same exact modes if you just replaced the green areas with a uniform average index. But the principle is the same, I guess. It's not band gap guiding. So that's important. You shouldn't always just assume things. And I didn't assume anything in this paper. The paper, they call it Holey fiber already. So if it was hollow core fiber, then you could be a bit more skeptical of the paper. But they do call it by a better name, Holey fiber. And if you look at the way they're calculating things, you see that there's no reliance on a band gap. So nothing wrong with the paper. For my own knowledge, I wanted to find out if that was the case, and I found that it was not the case. There's no band gap. And this is something you should probably look at in your own simulations as well when you're dealing with photonic crystals. So let's go back to the, not FDTD, but the mode solutions. So first I calculated these 3 modes, and the way I calculated, the way I made the geometry is by using scripting, right? So I wrote these long scripts, which is placing all these elements, and we can have these available for you guys if you want to try it out yourself. They're not super complicated, although starting a new scripting language always takes some time. But essentially, I'm just looping through a loop, and it's just creating these different objects depending on where it is geometrically and giving it materials. I also have set up a bunch of parameters here, right? So lambda is actually not wavelength, it's the pitch. And then some of these are like the diameters of the different hole structures. And this is, if you want to do like a really good simulation, a very complicated one like this, and make sure that it's very easy to use for simulating different things like the diameter length and stuff, you want to script it and you want to use user parameters. You could make so many mistakes if you were going through this and trying to change things by hand, right? So it's smarter to use a script and to use these variables that you can set up your geometry that way. I really suggest, once you have a simulation working and you want to sweep something like the diameter or the length of something, always use variables and a script. It makes, in the long run, everything so much easier. Right, so I ran the simulations. I used some tricks with boundary conditions to reduce the domain. Since it's symmetric in X and Y, in this case, you can reduce the domain by 4 and also kind of filter out some of the modes that you want. I can show you that in a sec. But first, let's look at some of the results. So this is the one with the symmetric center core, so it supports both an EY and an EX polarized mode. And this is the EX polarized mode that I have here. I'll put it as, you'll recognize it now. You see that the chosen field is EX, and it has a modal index, the top left here, very close to the one calculated by the authors in the paper. And similar results I got for the other cores. And now let's look at one of the more interesting structures, which is the multi-core structure, which is this one. A lot more complicated. Maybe I'll open it up as well to really show the structure here. Right, so you take the 3 cores and you set them side by side. And then just like in the first slides, that was showing the 2D mode solving, you got a symmetric and an asymmetric mode. We should find 2 different sets, one that's x-polarized, one that's y-polarized, and they should both have symmetric and asymmetric or even and odd modes that are that don't touch the other core that supports the other polarization. So here we have the structure, and then for the sets of results supporting the x-polarized mode, we see, and I'll choose the real field, not the amplitude, so we can see if it's even or odd. So here we have the even mode for x-polarized. You see that there's the y-polarized structure is over here. However, it's not really part of the mode field, right? The mode's confined to the other cores, the center core and the x-polarized core. And this is the even mode. So we've calculated the modal index. And then if we look at the next mode, we can see the odd mode or the asymmetric. And the difference between those, using that calculation I showed in the slide, on the second or third slide, in using the wavelength, you can calculate the beating length, or the coupling length rather, and you get about the same answer as in the paper, about 620 microns. And all you have to do is calculate 2 modes. Now, if we go over to the other result, I'll open up the y-polarized field mode structure. And look, this is the x-polarized, so you see that there's obviously some field in it, but the amplitude's much smaller than the EY, and the EY looks more clean because it's the dominant mode component. So again, for the EY, we have an even mode, and I'll just show it over like this to make it very clear. We have the even mode, and it's confined to the other 2 cores, the center core and the Y design core, and the x-polarized core is not really showing up in this picture. And you get a modal index for that even mode. And then also you get a odd mode that has the opposite, almost the opposite structure. It's not exactly the opposite, but it's close to the opposite. And again, you see that it doesn't really interact with the X core. Not a lot of the power is propagating in the X core. And then of course, the same way to find the coupling length of the structure for the Y polarization, you get the difference of these modal indices and then plug them into that equation. It's very simple, and you'll get the coupling length of about 630 or 640 microns, I believe. And that's about how you do that. It's not so complicated. Maybe it's not so clear because you don't see the whole geometry, but the actual, as long as you have the modes, the calculation is very simple to do. And I'll just show you, you see there's a third mode down here, and I haven't shown it because, right, it's not really part of the waveguiding structure. I used electric wall boundary conditions on this simulation domain. So the higher order modes will interact with these boundaries and create more of like a microwave type waveguide where, you know, if you had a microwave waveguide, the walls are usually part of the structure, and they're perfect conductors. Sometimes they're assumed to be perfect conductors. And then you have modes that all go all the way up to the simulation boundary. But we can easily show here that if we increase the boundary distance from the cores to the boundary, this mode would be farther and farther away. And it's not a true sort of optical waveguide because the field doesn't decay all the way to 0 near the edges. If you look at the pointing vector, it's even more clear that it's not really part of this optical waveguide. Okay, and that it's hopefully as simple as that. Once you calculate the modes, you have some understanding of how mode beating happens and how coupling works. You can calculate the coupling length, and you'd be able to design the structure with the proper lengths of these waveguides. And you could use this structure to couple out polarizations from the center core selectively into either one arm or the other, depending on its polarization. So of course, this could be used, you can see how this could be used in a communication system, right? That's using polarization mode or polarization multiplexing. You can double the communication speed, the bit rate basically, by modulating the two polarizations independently. Of course, it makes it a little more complicated, and you'll need something like this to couple out the two signals independently. There's still some time here, so maybe I'll talk a little more about how I split up that domain. But I'm not going to use these structures because these ones are actually pretty long to run, right? I wanted to match those results pretty accurately. So these ones actually take about an hour to simulate, which is pretty long for a mode problem. But I have an easier one here that doesn't take so long. I'll show you what I mean by using symmetric boundary conditions. If I have this set up right. So here I have the center core structure that supports the two different types of modes, right? X-polarized and Y-polarized. And right now it's set up so that all the walls are electric wall. And if I run this, let me just make sure that it should run fairly quick. There's a lot of elements in here to mesh, so the mesher sometimes takes some time in the bigger ones. You can see here we've found two modes. One that seems to be more X-polarized. They have the same modal index, right? So they're sort of degenerate, just like a single mode fiber, like a SMF28 from Corning has two single modes that'll be degenerate. And it also has this one, which has a major EY component, right? Same modal index, different polarization. But let's say I wanted to look at only modes that have let's say are symmetric over the X and Y axis for Y polarizations. I can set up the mesh. I can set up the boundary conditions to exploit that. So right now, if I do the mesh, preview the mesh, you'll see that it's meshing the whole simulation domain here. And again, this is a really rough mesh, so you'll see the modal indices aren't that close to what I got later with the more exact mesh, but this is just to show you quickly. So here we have the full structure being simulated. However, we know that it's symmetric X and Y, so why don't we use that to our advantage? If we want to have the proper mode that's EY polarized, we want to choose the min X boundary, so the boundary that's going up and down, to be symmetric magnetic wall. If we set it, we want EY polarized, so Y direction polarized. If you set it to electric wall, that's going to force the electric field in the Y direction to be 0 at X equals 0. But we're looking for sort of like a Gaussian field, right? The fundamental mode. So it should have a peak at the middle. So we don't want the tangential field to this boundary to be 0. We want it to be allowed to be any value. So that's why we're going to use a magnetic wall in the minimum X. But now in minimum Y, we want the Y polarized mode. So you'd want the EX field to be 0. I know it's sort of complicated, but this is how I think about it. There's different ways of thinking about it. You can also, they have sort of the dual relationship to the magnetic field, but I always think in terms of electric field. So that's one way of doing it. And you see if I mesh it again, you only now have a quarter of the simulation being meshed. And if we solve it, if I set up everything properly, we should only now get the EY polarized mode and then maybe one extra one that's interacting with the boundaries. right? So the major component here is the EY component. So that was a success. It plots it on the whole domain because it's usually you want the whole domain, but it's only simulating actually a quarter of the simulation domain, and that is very key, I think, to help some with the more complicated simulations, where you actually, if you want to get really high accuracy, you want to, use things to your advantage, like symmetry. And then it doesn't find the xpolarized mode because we chose the boundary conditions in such a way that that mode wouldn't actually exist in the structure. But it does find some higher order mode that's interacting with the boundary conditions at the top and the bottom. And so for the structures in the paper that were symmetric like this, the 3 cores that were individual cores, I used that to exploit it, right? I did the symmetric boundary conditions. For the ones that had the multi-core one, I couldn't exploit the full symmetry because you'll notice that it's not symmetric left and right, right? The yellow and the blue are different. However, it is symmetric top and bottom. So I could exploit one axis of symmetry, but I couldn't exploit the full different way. That's why you see the results. I opened up 2 different files for the results, because one was using one set of boundary conditions to get the y-polarized modes, and one was set up to get the x-polarized modes. And that leads me to my conclusion here. We went over some of those modeling techniques that I showed. I didn't get into so much detail because we're running out of time here, but I just showed you how I set up the geometry using scripting. I mean, very briefly. If you want to look in more detail, just email us. We can send the scripts to you to use if you want to do a crystal structure. I also showed some techniques to exploit the symmetry of the simulation, right? Using boundary conditions and the geometry of the structure to get higher accuracy, because you can use less degrees of freedom. And I didn't really get in detail how to mesh with the FEM, but if you're interested, you can try out an evaluation license on our website. I can definitely help you out with that. It's a little more complicated than our finite difference tools because it uses a triangle mesh, but it's not so complicated that you can't figure it out. Basically, you just control the triangle size instead of number of mesh points. That's basically it. Okay, so thanks everyone for coming by, listening to this webinar on the polarization mode splitter. And at this point, I'll just leave this reference up here for the video. People can pause the video when it's recorded and check it out. This application is also on our website, so you can check it out there as well. It's a very interesting one. I thought it was pretty neat. And if you have any questions, go ahead. We're going to have another poll here that Brian will start when I hand it over to him. And thanks a lot. So please, Brian, go ahead and start that last poll.
Thank you very much, Damien. Excellent presentation. And so this is the last opportunity for you guys to ask your questions live. If you think of some questions afterwards, you can always just email support@optiwave.com. Damien's on the CC list for it, so he can respond to you directly if you do email that address. And also, we've been doing quite a bit of webinars lately, and if you guys have any specific topics on any of the products that we have that you'd like to see a webinar conducted on, please let us know. You can submit webinar requests to info@optiwave.com, and we'll try to set up a webinar to address your simulation needs. So with that said, I'm going to go ahead and close the poll, and I'll let Damien wrap up the presentation.
Okay, looks like there's no questions yet. Again, if you have any particular questions, please email them to us at support@optiwave.com or at my email address, damien.merrick@optiwave.com. I want to thank everyone again for coming by, listening to this webinar, and I'll see you next time. Thanks a lot.